Well, these are called FRBs, fast radio bursts. They are among the biggest explosions of radio energy in the entire universe. They generate more energy than 1 billion suns.
That it will engulf the orbit of Mercury and Venus and come very close to Earth. So imagine looking on the horizon and sunrise is half the sky. Okay, that would be terrifying.
Betelgeuse, that bright star scientists have been studying for eons, has started acting up. It's not just twinkling, it's having some wild vibrations, and it's got everyone wondering what's going on up there. The night sky is our window to the vast universe beyond our world, but observations of Betelgeuse suggest it might go supernova or turn into a black hole. But could it affect us? And what would happen if it does? Join us as we take a look at the events happening around Betelgeuse, the supergiant, where we'll explore what's causing its erratic behavior and the danger it poses to Earth if it goes supernova. What is Betelgeuse? Betelgeuse is far from an ordinary star. It's a supergiant about 20 times more massive than our Sun. However, appearances can be deceiving. To us, Betelgeuse may seem like just another distant star, but its true status is profound. It's located more than 640 light-years away from Earth. While this distance might not sound too vast, in cosmic terms, it's enormous. Even if we could travel at the speed of light, which is currently impossible, it would still take over 640 years to reach Betelgeuse. Under normal circumstances, without such incredible speed, it would take more than 12 million years to make this journey. That's longer than the entire course of human civilization on Earth. This star is really something, and it's currently shaking things up in space. We often think of stars as just hanging out in the sky, minding their own business, regardless of how big they are. But Betelgeuse is here to show us that stars can be quite dynamic. Scientists are a bit puzzled by its vibrations. You see, Betelgeuse is what they call a pulsating red supergiant, meaning it's constantly changing. When it puffs up, it gets brighter, and when it shrinks down, it dims a bit in the night sky. These brightness changes happen over a pretty long time, from a few tens to hundreds of days. The cool thing is that Betelgeuse can go from being relatively bright to super intense, which is a pretty big deal. These brightness changes follow patterns, with the quickest one taking around 185 days, and the slowest, a whopping 2,135 days. Sometimes these changes can even get super predictable, and they call that the V-band magnitude. In February 2021, Betelgeuse had a bit of a light dip, kind of like a cosmic dimmer switch. It went from its usual radiance to a somewhat lower level, but it was still pretty bright in the night sky. Betelgeuse stands out not just because of its brightness changes, but also because it's rocking a unique reddish hue. This special hue comes from its cooler surface temperature at around 3,500 Kelvin. Now, that might sound a bit odd because, as we mentioned earlier, our Sun is smaller than Betelgeuse but generally brighter. That's because Betelgeuse's cooler temperature means it doesn't give off as much energy per square inch, making it seem dimmer, even though it's one of the biggest stars out there. Despite its pulsating nature, Betelgeuse has been pretty chill in the cosmic sense, staying relatively stable. Could an explosion be on the horizon? This is where things get a little tricky because Betelgeuse's behavior becomes more complex as it evolves. As a red supergiant, it goes through a natural progression. First, it consumes the hydrogen in its core through nuclear fusion, turning it into helium. This core depletion causes the star's outer layers to expand, signaling its shift into the red giant phase. During this phase, helium accumulates in a shell around the exhausted hydrogen core. The intense heat and pressure within this helium-rich shell initiate a secondary nuclear fusion process called helium shell burning. During this process, helium nuclei fuse, forming heavier elements like carbon and oxygen. This fusion then releases energy that counteracts the gravitational force trying to compress the star's outer layers. Unlike hydrogen fusion in the core, helium shell burning is less stable because it leads to periodic fluctuations in energy output. And it's tricky because these fluctuations result in instabilities within the star's structure, causing the outer layers to expand during energy buildups and contract during energy releases. These alternating expansion and contraction movements are observed as pulsations, which cause Betelgeuse's brightness to vary over time. The intense energy generated during helium shell burning can also create strong stellar winds, particularly in red supergiants like Betelgeuse. These winds carry away mass from the star's outer layers, contributing to the redistribution of matter and energy within the star and influencing its evolution. The rhythmic pulsations, akin to the star's heartbeat, correspond to changes in its luminosity when observed from Earth. While it's indeed possible that Betelgeuse's recent behavior is due to helium shell burning, astronomers need to take a few crucial steps before they confirm that. To unlock the mysteries of pulsating stars like Betelgeuse, they'll have to use various techniques, with photometry and spectroscopy being the standout players. In photometry, astronomers keep a close eye on how the star's brightness changes over time, which involves measuring the amount of light Betelgeuse emits at different intervals. So as Betelgeuse goes through its pulsations, its brightness goes up and down, giving astronomers some insight on the underlying processes responsible for these fluctuations. Photometry is the real star of the show, though, because it gives scientists a direct window into the star's dynamic behavior, letting astronomers track the nitty-gritty details of its luminosity. Meanwhile, spectroscopy offers a more nuanced perspective. It's all about analyzing the light emitted by Betelgeuse across a spectrum of wavelengths. This technique unveils vital information about the star's temperature, composition, and movement. You see, as Betelgeuse pulsates, its spectral lines shift and broaden, offering a peek into the physical conditions within its outer layers. These spectral changes are like cosmic fingerprints that reveal the mechanisms behind its pulsations. And by combining photometry and spectroscopy, astronomers piece together a comprehensive story of Betelgeuse's behavior. It's like putting together different parts of a cosmic puzzle to get the full story. These techniques allow them to uncover the star's secrets, from what's happening on its surface to its deep interior processes. And in the case of Betelgeuse, the more we learn, the closer we get to understanding the mesmerizing dance of this massive star. The insights gained from photometry's measurements of luminosity work hand in hand with the knowledge drawn from spectroscopy's spectral analysis. Together, these methods allow astronomers to unlock the connection between the star's internal mechanisms and its visible brightness changes, giving us a more comprehensive understanding of Betelgeuse's pulsating dance. However, to truly comprehend the inner workings of this celestial giant, astrophysicists dig in a little deeper by harnessing the power of computational models to simulate the star's internal dynamics and behavior. These models deal with various factors, from the complex equations governing the star's structure to the complex interactions of nuclear reactions and fluid dynamics deep within the star's core. These virtual models allow scientists to observe how Betelgeuse evolves and experiences its pulsations under various conditions, bringing them closer to deciphering the star's secrets. Bridging the gap between theory and observation is very important in this cosmic puzzle, as it allows scientists to form a clearer picture of what's happening on the surface of this star. But there's even more complex stuff happening within Betelgeuse's core. Stellar convection. Deep within the hearts of stars like Betelgeuse, a fascinating process called stellar convection takes place. This natural mechanism is important in transporting energy from the star's core to its surface, establishing a delicate balance between the star's internal processes and its outward radiance. Stellar convection is all about the movement of matter within the star in response to temperature variations. At the star's core, the site of intense nuclear fusion, substantial heat is produced. This heat causes the surrounding material to become hotter and less dense, leading to its expansion and upward movement towards the star's surface. Simultaneously, cooler material from the star's surface begins its descent towards the core. This cycle of rising hot material and sinking cool material generates convection currents, which act as celestial conveyor belts, transporting energy from the star's core to its outer layers. Convection promotes activity inside the star, and as hot material shifts towards the surface, it brings energy with it. When this energy eventually reaches the star's outer layers, it's radiated away as light, making the star appear brighter than it actually is. The cyclical nature of convection currents, with periods of increased and decreased energy transport, causes fluctuations in the star's luminosity, resulting in pulsations. But a completely different cosmic phenomenon can also influence the lives of these celestial duos in binary star systems: material transfer. Within these systems, two gravitationally bound stars orbit a common center of mass. A material exchange between them can have profound consequences, including the initiation of pulsations. You see, in a binary star system, two stars, the donor and the recipient, have a gravitational pull on one another, and based on their respective velocities and sizes, they may end up closer to one another. The gravitational interaction between these two stars can also trigger the transfer of material from the donor to the recipient. Naturally, gravity also has a significant impact, pulling material from one star and directing it in the direction of the other, adding to the complex dynamics at work in these binary systems. Astronomers continue to unlock the mysteries of this stellar phenomenon by combining observation and theory to better understand the complex processes influencing Betelgeuse's pulsations. These processes range from convection within its core to interactions with binary companions. The flow between the donor and recipient. As material flows from the donor star to the recipient in a binary system, a complex interplay of events unfolds. The mass transfer between these celestial partners has a big effect on the structure and behavior of the recipient star. When the recipient star receives an influx of mass, it experiences huge changes in its internal dynamics, because the additional material increases the recipient star's mass, thereby altering its internal pressure, temperature, and nuclear fusion processes. These modifications can serve as the catalyst for triggering pulsations within the recipient star. The disruption of equilibrium is the key to understanding this phenomenon, because the material inflow disrupts the recipient star's internal balance. This, in turn, disrupts and manifests as instabilities that eventually lead to pulsations, due to which the star's outer layers go through a cycle of expansion and contraction, resulting in fluctuations in its brightness. The origin of these pulsations is rooted in the recipient star's quest to find a new equilibrium among the various forces at play within its core. The powerful influence of gravity, radiation pressure, and internal nuclear reactions all contribute to these pulsations. But it's important to know about the broader implications of this process within binary star systems, because the exchange of material and the accompanying changes in the recipient star can also alter its evolutionary path. It diverts the star's trajectory, potentially leading it down a different route. Traditionally, the study of stars, even supergiants like Betelgeuse, has predominantly focused on them as individual celestial entities. The interaction and energy exchange between two stars were not commonly explored in historical astronomical research. However, with advanced telescopes and dedicated research teams, we have the tools and knowledge to dig deep into binary systems. Among the complexities of this binary ballet, there is an explanation that has been quietly looming on the cosmic stage. It implies that Betelgeuse's pulsations are more than just the ebb and flow of light. Instead, they could be hinting at a much more explosive event, the possibility of Betelgeuse going supernova. Betelgeuse, like other massive stars in the later stages of their life cycles, is engaged in a perpetual tug-of-war between gravity and the nuclear fusion reactions taking place in its core. This celestial balance has persisted throughout the star's existence, but it cannot last forever. Gravity, the unyielding force of attraction that governs the behavior of massive celestial objects, exerts a powerful pull on the matter within Betelgeuse, which, due to its mass, has the potential to collapse the star inwards. The star's core, on the other hand, is home to the process of nuclear fusion. Within this core, lighter elements like hydrogen undergo fusion reactions, transforming into heavier elements, most notably helium. These fusion processes generate colossal amounts of energy, which in turn give rise to outward pressure. The battle between gravity's pull towards the star's core and the nuclear fusion-generated pressure pushing outward is what keeps Betelgeuse stable during its main sequence phase. This phase represents a celestial balancing act, with the opposing forces maintaining the star's size and radiance. But as Betelgeuse nears the end of this main sequence phase, a dramatic transformation is inevitable. The balance that has sustained it for millennia will ultimately tip in favor of gravity. The star's core will no longer produce sufficient energy to counteract the gravitational forces at play. An inevitable supernova explosion. The star has reached a critical point in its life cycle at this point, known as the core collapse phase. It's characterized by the core's relentless contraction, because it becomes hotter and denser as the star's core shrinks. The temperature and pressure rise exponentially, initiating a chain reaction of increasingly intense nuclear fusion processes that cause the star to expand dramatically, marking the beginning of its final journey towards a supernova explosion. The signs leading up to a supernova event are unmistakable. Pulsations, increased brightness, and erratic behavior all indicate a massive star's end. For all we know, Betelgeuse's recent pulsations could be a precursor to the spectacular and cataclysmic finale. While this scenario might sound alarming, it's a natural part of the life cycle of massive stars. Betelgeuse's impending supernova, when it occurs, will unleash an extraordinary amount of energy and matter into the cosmos, seeding the universe with the heavy elements necessary for the formation of new stars, planets, and life itself. Ultimately, Betelgeuse's pulses represent a celestial metamorphosis, as the star is about to change from a bright supergiant to a supernova that will leave a lasting impression on the cosmos. The delicate balance that maintains Betelgeuse's stability and prevents it from collapsing under its own gravitational pull hinges on a perpetual interplay between gravity's inward force and the outward pressure generated by nuclear fusion reactions. As Betelgeuse consumes its nuclear fuel reserves over time, the equilibrium gradually tilts, and the diminishing hydrogen fuel supply affects the core's capacity to generate energy. With less nuclear fuel to sustain the star's energy production, the outward pressure weakens, allowing gravity to gain the upper hand. The star's core begins to contract under the relentless gravitational pull, so, as the core compresses, its particles move more rapidly, elevating the core's temperature. The core gets hot enough at this point to allow the fusion of heavier elements, like carbon and helium, which produces even more massive elements and releases energy. Helium and carbon fusion is a dramatic shift from the star's previous phase, which was dominated by hydrogen fusion. The ongoing fusion processes lead to the creation of progressively heavier elements, culminating in the formation of an iron core at the star's center. One special feature of iron is that it requires more energy to fuse than it releases. This important development represents a turning point in the star's evolution, a delicate energy equilibrium that has been maintained by previous fusion reactions is disturbed when an iron core forms and the star can no longer produce enough outward pressure. Eventually, gravity becomes stronger than all other forces, and Betelgeuse's iron core falls to the ground, which causes a supernova explosion. The collapse initiates a powerful shock wave that rapidly expands outward from the core, delivering a tremendous impact to the star's outer layers. This shock wave carries such overwhelming energy that it's capable of dismantling the star's structure and ejecting its outer material into space at astonishing speeds. Supernovae unleash an extraordinary amount of energy, often rivaling the brightness of an entire galaxy for a brief, intense period. These events can outshine countless individual stars in the surrounding vicinity. The resulting surge of light and radiation is not only a breathtaking spectacle, but also an invaluable source of scientific knowledge, offering insights into the extreme physical processes that occur in a star's final stages. Betelgeuse's current location, approximately 600 light-years from Earth, positions it so that a supernova explosion would be observable to us. But what would happen if it was closer? Well, it wouldn't end well, that's for sure. The resulting gamma-ray bursts are one of the most energetic and intense phenomena we observe in the universe. But what exactly are they? And what could happen if one happened closer to Earth? First things first, gamma-ray bursts come from some of the most extreme events in the universe. They often occur when massive stars, much larger than our Sun, reach the end of their lives in cataclysmic supernova explosions. The birth of one of these can be tied to a few different astrophysical processes. One common scenario is when a massive star exhausts its nuclear fuel. During most of a star's life, it maintains a delicate balance between gravity, which is constantly trying to crush it, and the energy generated in its core through nuclear fusion reactions. This energy pushes outward and keeps the star stable. But when that energy generation starts to wane, things get a bit unstable. As the star consumes its nuclear fuel, which is primarily hydrogen, this balance between gravity and the outward pressure from nuclear fusion begins to shift. There's less and less hydrogen available in the core for fusion, so energy production drops, and the star's core starts to contract under the relentless force of gravity. This contraction leads to a rise in temperature, as matter is compressed in the core. And when gravity wins this battle, it wins big. The gravitational collapse generates an enormous shock wave that races outward from the core, impacting the star's outer layers with incredible force. The energy involved is so staggering that it can rip the star apart, throwing its outer material into space at incredible velocities. Now, if a powerful gamma-ray burst occurred nearby, say within our Milky Way galaxy, while the supernova itself would be a spectacular celestial event, it would also have significant implications for us on Earth. Our planet has a protective layer in the stratosphere called the ozone layer. This ozone layer is essential for our survival, as it absorbs and filters out a considerable portion of the sun's harmful UV radiation. Because the intense gamma-ray radiation from such an event breaks apart ozone molecules, reducing the concentration of ozone molecules in the stratosphere, a powerful gamma-ray burst could potentially disrupt the ozone layer. And with a weakened ozone layer, more ultraviolet radiation would reach the Earth's surface. Ultraviolet radiation can have serious effects on human health, from increased UV exposure leading to skin damage and a higher risk of skin cancer, to fatal impacts on the immune system. But it's not just humans who would be affected. Marine life, terrestrial ecosystems, and plant growth would all be susceptible to ecological disturbances. Dangerously high UV radiation levels due to a weakened ozone layer could also lead to higher rates of cataracts in humans. And as the increased UV exposure weakens the immune system, it could leave people more vulnerable to a bunch of diseases. The impact of UV radiation extends to agriculture as well. UV-sensitive crops might experience reduced yields, altered growth patterns, and lower nutritional value. Such disruptions could have devastating implications for global food security. But the consequences of a nearby supernova and its associated gamma-ray burst go beyond health and agriculture. The intense radiation from the event could have a significant impact on Earth's technological infrastructure too. You see, in the event of a supernova, there's a release of a tremendous amount of energy, including high-energy particles and radiation, which can interact with Earth's atmosphere, creating a surge of energy. This surge generates bursts of electromagnetic energy called electromagnetic pulses, or EMPs. EMPs have the potential to disrupt or damage electronic systems, communication networks, and power grids. This disruption could extend to a wide range of electronic devices, from consumer electronics like smartphones and computers to more important systems like satellite communication equipment and medical devices. For instance, if a medical emergency were to occur during this time, contacting healthcare services and getting medical care would become nearly impossible. But one of the most concerning aspects of EMPs is their potential to affect power grids. EMPs generated electromagnetic energy may cause currents in transformers and power lines, which could damage equipment or cause complete shutdowns. This could cause widespread power outages, affecting homes, businesses, hospitals, and other critical infrastructure. But the consequences of EMP-induced disruptions don't stop there. In today's interconnected world, EMPs could have cascading effects. Financial systems, transportation networks, emergency services, and other infrastructure might be compromised, potentially leading to a global breakdown of essential services that could take several years to recover. We could also be looking at a possible disturbance to the Earth's atmosphere due to the influx of energy and radiation from the supernova. This could lead to altered weather patterns, shifts in precipitation patterns, temperature anomalies, and even some massive storms because of all the extra heat entering the Earth's atmosphere, which could potentially lead to short-term temperature variations. These variations could impact ecosystems, agriculture, and other sensitive environmental systems. When we think about the impact of all these disruptions on a global scale, it's clear that it goes beyond inconvenience. Sudden changes in temperature or precipitation might affect crop growth, yield, and timing. These disruptions could also have serious consequences for food security and supply chains, which would already be stressed due to increased UV radiation. In short, a nearby supernova and its associated gamma-ray burst would have serious implications for our planet. The rapid shifts in environmental conditions could challenge species accustomed to stable climate patterns and seasonal cues. Wildlife behavior, migration patterns, and reproduction may suffer as a result, and in some cases, if these effects persist for extended periods, there's a risk of certain species facing extinction. What if Betelgeuse turns into a black hole? The process of a star becoming a black hole begins when its core collapses beyond a critical density point, called the Schwarzschild radius, which signifies that the star essentially implodes under the overwhelming pull of gravity. In this collapse, the star's immense mass and gravitational pull become concentrated within an incredibly tiny space, forming what's known as a singularity, an infinitely dense point at the heart of the emerging black hole. Around this singularity is an invisible boundary called the event horizon, which marks the point beyond which nothing, not even light, can escape the intense gravitational grasp of the black hole. Now, if Betelgeuse were to transition into a black hole, it would appear relatively unchanged to distant observers until they interact with the event horizon. Unlike the explosive display of a supernova, creation of a black hole might not result in an immediate, visually striking event. But if such a transformation happened nearby, it wouldn't be silent or uneventful. The gravitational forces unleashed by the developing black hole would subject surrounding objects to extreme tidal forces, much more potent than anything we experience on Earth. Nearby celestial bodies like planets, moons, and asteroids could be torn apart or disrupted due to these intense gravitational forces, potentially leading to fragmentation and even collisions. To make matters worse, the massive black hole's gravitational influence would affect the orbits of neighboring celestial bodies. Planets and other objects nearby could have their trajectories altered, which could result in erratic paths, collisions, or, in extreme cases, ejections from our solar system. As Betelgeuse transitions into a black hole, the matter around it could be drawn in, forming an accretion disk. This disk would heat up and emit intense radiation spanning the electromagnetic spectrum, including X-rays and gamma rays. The emission of such radiation could have really serious consequences, particularly on the atmospheres of nearby planets. It may also impact any organisms or ecosystems exposed to this intense radiation. You see, the formation of a black hole is a remarkable process, but it comes with a few potential complications. When this transformation occurs, it releases a bunch of high-energy particles and radiation. Just like with supernovae, these energetic particles might sound interesting, but they can actually pose a threat to our technology, satellites, and even spacecraft that venture nearby. You see, delicate electronic systems can be disrupted or damaged by the intense radiation that's emitted during the formation of a black hole. So, it's not all just about astrophysical curiosity. There are real-world implications to consider. Black holes also have this freakishly strong gravitational field, mainly because they're incredibly dense and compact. Imagine if a black hole were to form near our solar system, coming from a star like Betelgeuse. Well, that gravitational pull could mess with the orbits of various objects, like planets, asteroids, and comets. This happens because gravity is a pretty universal force that operates across vast distances, so any massive object, like a black hole, can have a significant influence on the motion of other objects that are around it. Our solar system's balance is finely tuned, thanks to gravitational interactions between its components. For instance, planets are doing their steady dances around the sun due to the sun's powerful gravitational pull. But if a massive black hole suddenly joined the neighborhood, it could mess up the natural order because the rearrangement of orbits under the influence of the black hole could cause objects to be flung out of the solar system, collide with each other, or worse, fall into the black hole itself. This means orbits that used to be predictable could turn unpredictable and cause chaos due to the potent gravitational forces of the black hole. But that's not even worst part, because the reshuffling of orbits can send ripple effects throughout the solar system. Changes in the positions of planets and other celestial bodies could create new gravitational interactions that weren't there before. This could potentially destabilize the entire solar system, which, to put it simply, would be a complete mess. Now, let's take a breath and relax a bit, because Betelgeuse isn't exactly our next-door neighbor. In fact, it's quite far away from Earth, so when this star decides to go supernova, or potentially turn into a black hole, chances are most of us won't even know it's happening until things get back to normal. Life would carry on as usual. So, while these cosmic events are fascinating to talk about, they're not likely to disrupt our daily lives. But the big question is, would the Betelgeuse supernova even happen? Or is there a higher chance that it'll turn into a destructive black hole instead? Let us Let us know in the comments below and leave a like for more.